Our next speaker is Kevin Lynch. Kevin's Professor of Mechanical Engineering and he's Director of the Center of Robotics and Biosystems at Northwestern University in the USA.
Okay.
All right.
All right.
Thanks, Kevin.
Thank you. So today I'm going to talk about robot dexterity, but I'm going to talk a little bit about things that we've done and actually more about things that we hope to do, possibly with your help. So yesterday, Antonio told us about hands and grasping, and Alessandro told us about physical human-robot interaction, and Raj told us about human-robot coordination, and Alan told us about cobots. You're going to see all of those themes in today's talk. So in the spirit of celebrating our 40th anniversary, here's a video from a little bit more than 40 years ago showing the state of the art. This is a sophisticated tendon-driven robot hand performing in-hand manipulation. And then fast forward almost 40 years, and OpenAI used a sophisticated robot hand to do in-hand manipulation and achieved a modest success rate on solving a Rubik's Cube using some advanced machine learning techniques. So then 2 years later, as many of you know, OpenAI dropped out of robotics, and now it's seeking a $150 billion valuation. So one message you could take from this, but I hope you don't, is get out of robotics and just do AI by itself. But I think the message you should be taking from this is that robotic dexterity is fundamentally hard, and progress has been slow. So why is it hard? There's no silver bullet. So you can take the world's best AI machine learning and apply it to the state-of-the-art manipulation systems, and you're not going to solve the problem. So a few years ago, Frank Park and I wrote a textbook, and Matt Mason wrote what I thought was a brilliant foreword. So I'm just going to go ahead and read it to you. He was talking about robotics, but I'll replace with robotic dexterity. It's about turning ideas into action. What's the secret? Did some roboticist have a eureka moment? Did some pair of teenage entrepreneurs hit on the key idea in their garage? To the contrary, it's not a single idea. It's a substantial body of scientific and engineering results accumulated over centuries. So I think the message is we need advances in many different areas to be able to achieve the kind of dexterity that we see from humans. So today's talk is going to be about robot dexterity and two different paths towards dexterity. Autonomy, which is what we as roboticists often view as the holy grail, but human collaborative dexterity also, which averts or gets away from some of the most difficult problems, the harshest tests of autonomy. So back in the mid-90s, the word cobots was introduced to our society, and these days pretty much every industrial robot company sells something they call a cobot, but for my purposes, cobots are going to be things that you physically interact with to help you perform some sort of manipulation task. And the particular system I'm going to be talking about is a team of mobile robots, or mobile cobots, that work with people for manipulating large objects. So the Mocobot team for us is intended for large objects, distributed contact because maybe the object is heavy, or it's fragile, or it's got internal degrees of freedom that you have to control. And the tasks you want to perform are difficult to automate or would otherwise benefit from human input. So the requirements that we have for a Mocobot team is that they're good at end effector force control. They offer passive compliance for the safety of the payload and the human, and that they can manipulate all the degrees of freedom of the object. So our first attempt to build a robot that satisfies these conditions is called the Omnid Mocobot, and it's got a 3-degree of freedom delta parallel manipulator driven by series elastic actuators, and that's what allows us to get good force control at the end effectors, but also get this passive compliance at the frequencies, the bandwidths, what you can't achieve through active control. You still have some safe passive compliance. So with a group of these, at least 3, you can manipulate objects with 6 degrees of freedom or more. And so here's a very simple control mode enabled by these robots. All they're doing is canceling gravity on the payload. So here the operator is manipulating the payload in 6 degrees of freedom. It weighs about 15 kilograms, and it's very intuitive. They don't have to learn to do this operation, right? So there's no learning of teleoperation, for example. And it's not just for one human. You could have multiple operators. You can have objects like you see here with internal degrees of freedom. and again, no learning curve. And this is a video of my student Lynn using the system to perform an assembly task where she's getting direct haptic force feedback from the interaction, and that's very intuitive how to use that for corrective actions. And not only that, the robots can be observing what she's doing for the assembly operation and then using that to learn to perform the assembly themselves. So there is a path to autonomy here from programming from demonstration. So I want to come back now to autonomy after that foray into human collaboration. And when I think about autonomous manipulation, I break it into two categories: non-prehensile manipulation, so no grasp, and prehensile manipulation. And non-prehensile manipulation is something that you see in nature and in entertainment, and it's something that I personally have been fascinated by for many years because it offers the opportunity to use dynamics to control more degrees of freedom of objects than the robots have actuators. And you can see examples of that up here, generating a vibratory vector field on the surface of an object using vibrations and friction, or pushing multiple objects simultaneously. But today I want to focus more on prehensile manipulation, and to motivate this, let's think about what you get when you're trying to build a manipulation system in your lab. You order a robot, it comes like this, it's got a wrist but no end effector. So the first thing you do is you add some sort of gripper or perhaps suction gripper, where at best you're hoping to immobilize an object to the end effector of the robot. But that precludes other sorts of dexterous manipulation like shuffling cards or tying a knot or using tools, where all of these things require in-hand dexterity, so usually motion of the objects relative to the hand during the manipulation. So we are now beginning to address this challenge through a new center that the National Science Foundation just funded this month, actually, called Human Augmentation via Dexterity, or HAND. And so this is the portion of the talk where I'm telling you things that I hope we'll be able to do, but don't know how to do yet, which is actually one reason why I want to talk to you all about it. So the idea is, instead of the out-of-the-box we saw before, this is what we'll get out of the box in the future. When you open up your dexterity system, you'll get 2 tactile sensor-enabled robot hands, stereo vision, a multimodal user interface, and some inexpensive manipulanda so you can start working with the system immediately right out of the box. So after you've uncrated it, you mount the hands to your robot arms, you download the latest skills from the internet, and now you perform your first demo. So the first demo might be to put a jar and its cap somewhere in the robot's workspace and have the robot reach out, screw the cap on, take it back off, and be able to do this repeatedly. And if it can do that, then you have some confidence that your system is set up properly. From there, you may move on to skills that are more relevant to you. Then you'll get into using the user interface for teleoperation and eventually for behavior cloning. And then from there, creating new skills that you can share with the community. So our goal really is to make dexterous robots as easy to use as teenagers can use drones. So to get there, these are the research thrusts of the center. First the hands, then the skills, and then the human interface for programming. For hands, we're looking at creating soft, tactile sensing skins, new kinds of actuators, and then the design to incorporate these new technologies into robot hands. For skills, we're talking about developing new simulation system for high degree of freedom soft hands, a skill library that others can contribute to, and a behavior cloning pipeline to take from the human interface and transfer skills to the robot. And then for the human interface, we're looking at the multimodal interface and low-code programming so that anybody can use the system, not just trained PhDs. So all of these things meet at our test beds, and one of our test beds is we call DexNex, or the Dexterity Nexus. This is actually a mashup of the Avatar X Prize winner from Nimro, as well as the tactile telerobot. So you can see the user here is wearing an interface that allows him to see what the robot is seeing and feel what the robot is feeling, and then through that teleoperate the robot and then eventually be able to transfer skills. But there's a number of limitations to the system as it currently is, which forms our research program. We'll also be working with innovation ecosystem partners to address high-impact applications in manufacturing, assembly, and caregiving. And why are we doing this now? Well, you can see that there's a dramatic disparity in the growth of productivity in small companies versus large companies that can currently invest in robots. And there's growing lack of workers in manufacturing and healthcare. And these are huge businesses which have the cost of the economy of over $1 trillion, the US economy. So we have a great team, but we need more help. So if you're interested in being involved or you want to learn more, please visit our website. And with that, I'd like to wrap up by thanking the organizers of ICRA 40, the students of the center, particularly Lynn Liu, who's here and who's now the lead of our collaborative manipulation project. And I'd like to thank you for your attention.
Thank you, Kevin.